Okay, we're going to start off chapter 10 here, and the main concept involved is going to be something we call torque. And torque, for simple terms, is basically what makes an object rotate. And we just worked with some quantities of rotation and angular quantities last chapter, which will eventually kind of all come together here with torque in chapter 10. But in just common everyday terms, torque is not only a force you put on an object like a lever or a wheel to rotate. It's the force and where and how I put it. So thinking in terms of a lever, a very simple one here. Let's say we have a pivot point, maybe like a hinge of a door opening is the example I'm going to use through a lot of this. And this is my lever on that hinge or the door on that hinge from maybe a top view. When I say where we put that force, that's a radius, and what I mean by that is it's a radius from the pivot point. So if I place my force here, somewhere along down the lever, the radius is simply the direct measurement from the pivot point of my lever, if this is the wheel, it's the central axis of the wheel, to where I applied that, R. And how I apply that refers to the angle. Did I push perpendicularly? Did I push at some angle? And we measure that angle to the lever arm itself. Now, as a formula, torque is, as a vector, because it does have direction, is equal to a cross product of this R cross F. Now, when we use cross products, as you may recall, we get the directions from them through the right-hand rule, which we'll apply in class later. Now, you may recall from very earlier in the year when we learned about cross products in our intro to vectors, is that the magnitude of a cross product is equal to the two vectors involved, their magnitudes, multiplied times the sine of theta. Sine of the angle between them, and that would be here on our diagram. And this is going to be the most useful form of the equation, because most of the time we are focusing on the magnitude. And then if we want the direction, we'll just apply the right-hand rule to the direction of rotation about the axis or pivot point. There's another variation of this formula that says torque is equal to F times lever arm length L. I'm going to use a cursive looking L so we don't get it confused with another L later on in this chapter. And L is defined as the lever arm length. And through a few examples coming up with some diagrams, we'll describe what exactly that means. L is really just a part of this formula. L is defined as R sine theta. And overall, the units for this new value we're learning called torque is Newton meters, because you can see it's going to be a force times a radius. Force in newtons, a radius typically in meters, so the units we'll note are going to be Newton meter. And by the way, you might notice that torque's really not a T, it's actually the Greek symbol ta, so we don't get it confused with time or time period. Now let's see how this applies to a specific scenario. And first we're going to take, pretend this is a top view of maybe a hinge and the lever is a door somebody's walking over to push on. Now, unless you're impeded by something, it's most natural to push a swinging door perpendicular. So if we do that and apply our formula for the magnitude of torque equals Fr sine theta, what we'll soon realize, if you don't already, is that if theta is 90 degrees, or perpendicular, the sine of 90 degrees is equal to 1. Therefore, if the push or pull involved in the torque is perpendicular, torque is just equal to F times R. And we get our maximum torque out if we use the longest R possible. So that's why it's most typical and common sense to place your force on the complete opposite side of the hinge. Now, in this one, the lever goes out a little bit more. If I wanted even more torque, I'd come out here. But think about any door you ever saw made, the handle is always as far over as possible from where the hinge is. That gives me a bigger R. The bigger R times whatever force I put on it, and the fact it's perpendicular will maximize my torque. If this angle is anything other than 90, then this will not be 1, it will be a fraction between 0 and 1, therefore reducing my overall torque. So I always want to, when I rotate something, the best thing to do, especially if my force is limited, is to increase my R as much as possible and push perpendicularly. Now, let's take a look at what lever arm length means in this scenario. Well, it's really simple in this one. Remember, L is really just a chunk of this formula, R sine theta. So again, if theta is 90, what that tells me is L equals R. There's no difference between the lever arm length and the radius itself when I push perpendicularly. So L might be a little bit better explained when it's not this convenient scenario. So let's take almost the same situation, but now we're going to make an angle of, let's call it 30 degrees for ease of some numbers in our example. And by the way, it doesn't matter which angle would you use, 30 or its supplementary angle of 150, because supplementary angles will have the same values when taking the sine of them. Sine 30 is a half and sine 150 is half, so it really does not matter which direction you measure that angle from, formula-wise. Okay, so taking the same situation, the only thing I'm changing is theta. I'm now not perpendicular. So if I did FR sine 30, well, sine 30, I picked 30 because it's convenient, it's a half. So torque would equal FR times 0.5 or divided by 2, whatever way you want to put it. So if I pushed exactly as I did in this scenario, with the same force at the same radius, but this time I changed that angle then to 30 degrees, then I only get half the torque out. And therefore I won't rotate that object as easily. And a word we often use, and this will be better explain that L value, is I really lose leverage. And when I say I lose leverage, we're really talking about that term L, lever arm length, which remember is equal to R sine theta, but this time theta is 30. So in this case, L is not equal to R. So if I measure from here to here, that's still R. R is always the finite measurement from the pivot to where the force is placed. But L now is not equal to that. So what does L mean? We don't see it anywhere here, and that's what we're trying to explain. So L is going to be equal to R over 2. And what L really represents now is a position we'll draw on our object. Well, R over 2 would be approximately right here. So when my leverage is lost due to an angle that is not 90 degrees, not perpendicular, it is as if I placed this force perpendicular back here at a shorter R. So L would be half of R since we had an angle of 30 degrees. So again, it's like it would be the equivalent of using the same force back here perpendicularly at a much shorter radius, hence losing lever arm length, or losing, as generally we say it, leverage. That's what L means. So L is different than R when we are not at 90 degrees. And it just means some position back here less than the full length of R, a fraction of R, as if we would have pushed back here to yield the same result or the same torque. And very soon we'll be applying all these equations in a multitude of problems and within bigger equations.